Okay, chapter 10. We should be done this on Wednesday, so Thursday we'll start our last chapter, chapter 11, on permutations and combinations. So chapter 10 deals with functions, and we're going to look at different operations on these functions, starting today with some differences of functions. When you take one function and you add it to another, and we'll look at what that looks like when it comes time to the graphs of them as well as the equations. So this first example says consider those functions. Is this the first page on yours? Or is there that graphing activity to start with? Yeah, that's good. Okay, so we've got two functions f and g. Then it says determine the equation to the function h at x, which is f plus g at x. So what f plus g at x means is it means f at x plus g at x. That's what that means. F plus g at x means you're going to add the two functions together. You're going to add f and g together in terms of x. And so it'll be f, which is 2x plus 1, plus g, which would be x squared. And normally we write these polynomials in order of descending power, which means you'll have the x squared term first, followed by the x term, and then the plus 1. Now it asks us to sketch all three on the same grid. We're going to sketch f at x, we're going to sketch g at x, and then we're going to sketch h at x. So first, f at x. F at x is a linear function, 2x plus 1. So that's a line that has a y-intercept of plus 1 and a slope of 2. Right, that is in slope-intercept form, y equals mx plus b. B is the y-intercept, which is plus 1, and the slope is 2. And remember, you want slope in terms of a fraction because slope is rise over run. So 2 would be 2 over 1. Rise 2, run 1. Rise 2, run 1. We can also rise negative 2 and run negative 1. Rise negative 2 and run negative 1. You can do that as well. But all these points should line up. And we have our line. Y equals 2x plus 1. And our graphs always have arrows on the end because they go forever, following that same pattern. Right, so there's our first equation. Our second equation is g at x, which is just x squared. So we start with values of x, we square them to get y. 0 squared is still 0. Oh, that spot. It's in the wrong spot. There we go. When x is 1, 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. So this is the graph of y equals g at x. Right, so that's g at x. This is f at x. And then it asks us to graph h as well. And the equation we got for h at x is x squared plus 2x plus 1. Now that could be rewritten in factored form. That would be x plus 1 all squared. If you factor x squared plus 2x plus 1, the factors there are x plus 1 all squared. Which means when we graph this, it is the graph of y equals x squared shifted 1 to the left. That positive 1 inside the bracket represents an h value. And remember, the value of h is always the opposite of what it appears to be. Remember, h is hooked onto the x with a plus or a minus. Whatever happens to the x happens to the x minus h. In this case, they are both squared. So this would be an h value of -1, which means the graph would shift 1 to the left. Compared to y equals x squared, which we just did, we're going to shift it 1 to the left. All the points will go 1 to the left. And so this is the graph, the second one. Or I should say the third graph, the graph of h, which is f at x plus g at x. So let's look and see what's happening here and see if there's a way we can go from the first two graphs to the second, which actually, without actually drawing all these graphs. If we can just end up with the third graph without graphing the first two. And we'll do this by setting up a table of values. So I'm going to have these values of x, -2, -1, 0, 1, and 2. If we take the y values for each of these graphs, the first graph was f at x. So we didn't use a table of values to graph it, we used slope-intercept form. But we also could have used this table of values. When x is -2, and I let x equal -2 in the equation 2x plus 1, 2 times -2 is -2, -4, excuse me, plus 1 is -3. When x is -1, 2 times -1 is -2, plus 1 is -1. When x is 0, 2 times 0 is 0, plus 1. 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. So those would be the points on 2x plus 1 using the table of values. Now for g at x, which is x squared, all the x values get squared. -2 squared is 4, -1 squared is 1, 0 squared, 1 squared, 2 squared. And then finally for h at x, if I use the original equation, x squared plus 2x plus 1, or if I use the factored one, which is a little bit easier, when x is -2, -2 plus 1 is -1, squared is 1. When x is -1, -1 plus 1 is 0, squared is still 0. When x is 0, 0 plus 1 is 1, squared is 1. 1 plus 1 is 2, squared is 4. And 2 plus 1 is 3, squared is 9. And so that would give us the points for h at x, which are on the blue graph. However, if you look at the y values for f, g, and h, you should see that if you add the y values for f and g together, it gives you the y values for h. -3 plus 4 does equal 1. -1 plus 1 does equal 0. 1 plus 0 does equal 1. 3 plus 1 does equal 4. And 5 plus 4 does equal 9. So because h was derived by adding f and g together, you can get the equation for h by adding f at x and g at x together. But now we see that we can get the graph of h by taking the y values from f and g. For each different value of x, take the two y values from f and g and add them together. And again, the reason why they're added is because h is f at x plus g at x. So you're adding the functions together, you're also adding the y values together. Okay? So it asks us to state the domain and range for h. The domain would be all real numbers. The graph goes to the left and to the right forever. There's no restrictions on x, so using interval notation, -infinity to +infinity. And for our range, it does have a minimum value of 0 up to +infinity. Notice that we have a square bracket on the 0 because it's included. but not on infinity because it's not. Okay, so there's the domain and the range of H. Now, if you look at the domain and range of F and G, for F, there are no restrictions. For G, you did have a restriction on the domain, and that was that y had to be greater than or equal to 0, right? And notice that the domain and range for H are connected to the domain and range of G. Basically, any restrictions on G and H will show up in, any restrictions on F and G will also show up in H. And we have a restriction on the range for G, and that is that it has to be greater than or equal to 0. And that's also the same restriction on H. Both graphs F and G have no restrictions on X. And that's why there's no restrictions on X for H either. Right? So they are connected. Part D says determine the values of F, G, and H when X is 4. So first F at 4 will be 2 times 4 plus 1. 8 plus 1 is 9. G at 4 is 4 squared, which is 16. And H at 4, if I use that equation above, the x plus 1 all squared, 4 plus 1 is 5, squared is 25. And again, note that if you add F at 4 and G at 4 together, 9 plus 16, you get H at 4. You get 25. So that always works. So how would you know what to do? Well, it depends on what you're given, right? If you're given the equations and you're asked to find an expression for F plus G at X, well, you just add the equations together. If you're given the graphs originally and you want to sketch the graph of, let's say, the sum of the two functions, then we can do what we've just talked about. Take the y values for each x value, take the two y values, add them together. That'll give you your new y value. So we'll do some of that. It all depends on what you're given. Like in example 2. In this case, you're given the graph of f and g. You're given the graph of f at x and g at x. You want to sketch the graph of h at x, which is f plus g at x. So we will get that by adding the y values together. So if I take my first set of y values that are noted on my graph, they are when x is negative 4. When x is negative 4, f has a y value of negative 3. G has a y value of positive 1. So negative 3 plus 1 is negative 2. The x value doesn't change. It's still negative 4. But our new y value is found by adding the two y values together. The next set of points we have noted on here is when x is negative 3. On f, the y value is negative 2. The x value is 0. That is the x-intercept of the y value for g is 0. That is the x-intercept of that graph. And so negative 2 plus 0 is negative 2. Negative 2. But here the y value, or x value, I should say, was negative 3. So there's that point. The next set of points I'll use are when x is negative 1. You're going to have negative, and actually I did this. When x is negative 1, notice that when x is negative 2, note that the values of y are the same. They're both negative 1. That's that point right there. But we're still find our new y value by adding those y values together. Negative 1 plus negative 1 is still negative 2. So you're seeing a pattern here. It seems like all of the y values, when you add the two y values together from f and g, all the y values appear to become negative 2. That'll work for this point right here, these points. Negative 2 plus 0 is negative 2. The y-intercepts are negative 3 and positive 1. negative 3 plus 1 is still negative 2. When x is 1, you have y values of negative 4 and positive 2. Well, negative 4 plus positive 2 is still negative 2. When x is positive 2, you have y values of negative 5 and positive 3. Negative 5 plus 3 is still negative 2. So we have that pattern that we talked about in this case because f is a line. Its rate of change is a constant. It's always going up by the same value because it's a line. Same thing with g. The rate of change is a constant. The slope is negative there, but it's still a constant. And so because of that, the sum of the two will be a constant as well. And we get that line y equals negative 2. So if you have the two graphs and you want to find what the graph looks like for f plus g at x, just add y values together and you'll have the new y values for the new graph. In this case, we weren't given the original equation, so we're not asked to find the new equation. We could figure out what those equations are, but we're not asked to. We just asked to sketch. So what's different about this one is now note it's f minus g at x. So now we have to subtract the y values, okay? And so I'll just do some writing on the side here. So when x is negative 4, to find m at negative 4, I have to go f at negative 4, subtract g at negative 4. So on the f graph, when x is negative 4, we see the value of y is negative 3, minus on the g graph, when x is negative 4, the value of y is positive 1. And negative 3 take away 1 is negative 4. So that's that point right there. All right, what about m at negative 3? So we take the f value when x is negative 3, and that is negative 2. Oh, I should write this out. So I'm going to do f at negative 3, take away g at negative 3. And again, now the f value at negative 3 is negative 2. The g value at negative 3 is 0. And negative 2 take away 0 is negative 2. So the first one was negative 3, take away 1. That would give us negative 4. The second one is negative 2, take away 0. That gives us negative 2, which is that point right there. The next point we have here is when x is negative 2. So for m at negative 2, we'll take f at negative 2 and subtract g at negative 2. F at negative 2 is negative 1 minus g at negative 2, which is also negative 1. And in this case, the minus minus becomes a plus positive. It becomes negative 1 plus 0, or plus 1, I should say, which is 0. So that is that point right there. So we can already see that this is going to be a little bit different than the last one. The last one was a horizontal line. We have the line y equals negative 2. The difference, though, there is that we were adding the y values together. Now we're subtracting them. So there's still a pattern here, but it's just a different pattern. Right? This line looks like it's going to have an actual slope, whereas the previous one had a slope of 0. So let's continue on and see if the pattern continues. If I want to find m at negative 1, that'll be f at negative 1, take away g at negative 1. F at negative 1, on the f graph, that's 0. Take away g at negative 1, which is negative 2. And the minus minus becomes a plus positive. So you get 2 plus 2, which is positive 2. So that's the point negative 1 comma positive 2. That point lines up with the previous three. Follows the same pattern. Let's do a few more. Let's do m at 0. So that'll be f at 0 take away g at 0. F at 0 is 1. Take away g at 0, which is negative 3. And again, the minus minus becomes a plus positive. 1 plus 3 is 4. So there's that new point, the point 0, 4. Again, it lines up with all the other ones. Let's do one more. Let's do m at positive 1. So that'll be f at 1 take away g at 1. On the f at x function, f at 1 is 2. On the g at x function, g at 1 is negative 4. Again, the minus minus becomes a plus positive. 2 plus 4 is 6. So that gives us the point 1, 6, which again lines up with all those other points. So because both f and g were changing at a constant rate, m also changes at a constant rate. So there's that line. Now, I mean, it's not necessary to do all this work that I did over here, but I did it just to reinforce what's happening. How do we get all the y values for the new graph? Well, subtracting the two y values from the original. You do have to be careful, especially with subtraction, that you do it in the right order. If you're adding, it doesn't matter. F plus g is the same as g plus f, but subtraction definitely makes a difference. Right? If it says f minus g at x, then you have to go f at x take away g at x in each case. Looking at example 3, the only difference here is that the first graph is a radical function, but doesn't change the way it's done. If you want to find h at x, which is f minus g at x, so that'll be f at x take away g at x. The other thing you have to be careful about here is that to show that we're subtracting all of g at x from f at x, we put the g of x in brackets, which is important because you now have a minus sign in front of the bracket, which will change all the signs inside that bracket. It'll become a negative x and a positive 2. So there's that equation. And again, we're given the graphs of f and g on the same set. Now we want to sketch h. And again, have to be careful that we do it in the right order. In every case, it has to be f at x take away g at x. Also note that the graph of f at x has restrictions. This graph starts at the point 0, 1, and then goes off to the right. So because the restriction here is that x has to be greater than or equal to, I think I said 0, 1, it should have been 1, 0. But because the domain of this graph is that x is greater than or equal to 1, the smallest number we can start with here is positive 1. If I try and do f at 0, well, it's not part of this graph. So we can't get an answer for that. Because I have the restriction on f, that x must be greater than or equal to 1, I'll have to have the same restriction on h. So the first value of h I can find would be h at 1. That would be f at 1 take away g at 1. So f at 1 is 0, g at 1 is negative 1. So it'll be 0, take away negative 1. Again, the minus minus becomes a plus positive. So that'll be the point 1, 1. Okay, so that's that point right there. Next, h at 2 would be f at 2 take away g at 2. F at 2 is 1. Take away g at 2, which is 0. We get the same value for our second point as we did our first point. Let's see if that pattern continues. What about h at 3? So that'll be f at 3, take away g at 3. On the f at x function, f at 3, well, we've got a bit of a problem here because we don't know exactly what the value of y is at positive 3. In fact, if we look at our graph, it looks like the next place where we know what the value of y is on f is actually when x equals 5. So I'm going to skip to that one. I'm going to do h at 5, which will be f at 5, take away g at 5. F at 5 is positive 2, take away g at 5, which is positive 3. And now 2 minus 3 is negative 1. So the 0.5 comma negative 1 would be right there. Okay, so what's the next point we can use? Well, it looks like when x is 10, we can see what the value on f at x is. So let's do that as our last point. H at 10 would be f at 10 take away g at 10. So f at 10 appears to be positive 3. Take away g at 10, which is positive 8. So that gives us negative 5. 10 comma negative 5. Let's see if we can nail down one point, and we'll have to do some estimation here to do that. So I went from f at, or h at 2 to h at 5. What if I try to do one number in between, just so I can have a better idea of what's happening here? Where is the graph transitioning? These first 2 points line up to be a horizontal line, but then the next 2 points go downward. So let's see if we can guesstimate what h at 3 is. So again, we're going to have to do some estimation here. F at 3 appears to be at about 1.5. It might be a little bit less than 1.5, but I'm going to go with 1.5 as an estimate. Minus g at 3, well, that's exactly 1. And so that gives us 0.5, approximately. The 0.3 comma 0.5. So based on that, and if I wanted to, I could also do one more point where, let's say, x equals 4. However, this last point I just put on here appears to line up with these other two that I already had. So because of that, this first part is horizontal, and then it starts to go down. There will only be an arrow on the right side of this because we can't go left forever. The original graph of f has that restriction that x has to be greater than or equal to 1. So that is also the same restriction for h. X must be greater than or equal to 1, which is what C is asking us to state. So 1 to positive infinity would be the domain. Yes? Can't hear you. Which one is what? They're labeled on the graph. F is the curve, G is the line. The graph of what?
Graph of G.
Okay.
So negative 2 and out. The other one not go below negative 2.
No, it wouldn't. Because whatever restrictions there are on the original graphs, I think you're going to see that there are always going to be the restrictions on the new graphs, whatever those restrictions are. Okay, so now part D says use the graph to approximate the range of h at x. Okay, so let's look at our graphing calculator and let's put h in there and see what it looks like. So we've got the root of x minus 1, and then we'll have minus x plus 2. So if I set my windows to their standard settings, looks like I have a second equation in there. Yes, I do, so let's take that out. So that looks very similar to what we have drawn on our paper. Okay, but let's change our windows just a little bit so we can clearly see what's happening at this starting point here. So for x, I'm going to go from, let's say, negative 1 up to positive 4 and a scale of 1. And for the y values, let's go from negative 1 up to positive 2 and a scale of 1. So I'm just changing the windows so I can have a better look and see what's happening, especially where this graph first starts out. So now when I hit graph, look at it now. It actually looks like there's a bit of a curve here between positive 1 and positive 2. So let's find out what the value of h is at, say, 1.5, between positive 1 and positive 2. So let's find h at 1.5. And again, we're going to use some approximations here, but let's see what we get. So that'll be f at 1.5 minus g at 1.5 . So for f at 1.5, we can use the equation because we have it, right? So we actually don't have to do any estimation if we don't want to. 1.5 take away 1 is 0.5. And so we need to take the square root of that, the root of a half. Is 0.707. So this will be 0.707. Take away g at 1.5, and again, because we have the equation, we can use that. When g at x, which is x minus 2, when x is made to be 1.5, you'll get 1.5 take away 2, which is negative 0.5. So again, the minus minus becomes a plus positive. So we're going to have that 0.707 plus 0.5, which is approximately 1.21. So it did go a little bit higher. So this part of the graph actually comes up a little bit and then goes down. And assuming that the highest point is between 0 and 2, or 1 and 2, I should say, which is at 1.5, that would make our maximum value 1.21. But to make sure, we can use our graphing calculator to make sure, see if that is actually the highest point. Let's find our maximum. Let's go second function trace. And again, we want number 4 here, which is the maximum. I'll put my left boundary at 1, my right boundary at 2, and it's actually at 1.25. So using the graphic display calculator, the maximum point is 1.25, and it occurs when x is 1.25. What we just did just now was using x equal 1.5. And we got a y value of 1.21. But our calculator tells us that that's not the maximum point. The maximum point is actually at 1.25 comma 1.25. So using the graphic display calculator, our maximum is at 1.25 comma 1.25. Which means that our range would be that y must be less than or equal to 1.25, or using interval notation, from negative infinity to positive 1.25. So this could only be found by using the graphing calculator. So not only can we use the calculator as a check for some of these questions, but in some cases you need to use the graphing calculator in order to get your answer. So here's another one that involves subtraction. Consider f at x, which is the absolute value of x, g at x equals x minus 5. What is that equation? F minus g at x. So that would be f at x minus g at x. F at x is the absolute value of x. Now again, we have to subtract all of g. So I put g, which is x minus 5, in brackets. And then when you remove the brackets, it changes all those signs. The x becomes negative, the 5 becomes positive. So that would be the equation of h. Now we're given the two graphs of f and g. We want to use them to sketch the graph of h. So I've got arrows on these graphs everywhere, but I've just kind of run out of room here for g, right? That's where this graph ends, down there at the bottom. However, I do have my equations that I can use if I need to do each of these, okay? So let's first start by finding h at negative 4. I can't read it off the graph of g, but I've got the equation. So this will be f at negative 4, take away g at negative 4. The equation for f is the absolute value of x. So it'll be the absolute value of negative 4, which is 4. Take away g at negative 4, which I can read from the graph. That's positive 4. So that gives us 0. The point negative 4 comma 0. What about h at negative 2? So I skip negative 3. Doesn't really matter. I'm just spreading it out a little bit. So f at negative 2 would be the absolute value of negative 2, which is 2, minus g at negative 2, which we can get off the graph. That is positive 2. And again, that gives me an answer of 0. Right? What about h at 0? So that'll be f at 0, take away g at 0. F at 0, we can read that off the graph if we wanted to. Oops, I did that. Hang on, guys. I got some wrong numbers here. I was using the wrong graph to get g at negative 4. G at negative 4, I need to use the g at x function. I just want to check to make sure I've got, and I don't have it right. So let's fix that. G at negative 4 would be negative 4 take away 5, which is negative 9. So I apologize for that. I was using the graph of f for my g values when I was looking at the graphs. So if I want g at -4, it'll be -4 take away 5, which is -9. So it'll be 4 take away -9, which is plus 13. So sorry about that. I don't have room on my graph for that because my y value only goes up to +8. So let's do the second one. The second point, we'll fix that one. So h at -2, that part is, or f at -2 is 2. But g at -2 would be -2 take away 5, which is -7. So 2 minus -7 becomes 2 plus 7, which is +9. Don't have room in my graph for that point either, because my y value only goes up to +8. We can kind of estimate where it would be, the point -2 comma +9. So it'll be approximately up there, somewhere up there. Okay, f at 0, take away g at 0. F at 0 is 0. Take away g at 0, which is -5. And the minus becomes a plus positive. So that'll be the point 0, 5, which is that point right there. So now let's do h at 2. So that'll be f at 2, take away g at 2. F at 2 is 2, minus g at 2, which would be -3. The minus becomes a plus positive, and we get +5 there. So point 2, comma, +5. So there definitely was a decrease from the first point to the second point, but now the third point has the same y value as that second point. So let's see if that pattern continues. If I have h at 4, so that'll be f at 4, take away g at 4. F at 4 is 4, minus g at 4, which will be 4 take away 5, or -1. And the minus becomes a plus positive. So that is the point 4, comma 5 as well. Let's do one more. Let's find h at 6. So that'll be f at 6, take away g at 6, 6 take away 1. And x is 6. G would be 6 minus 5, which is 1. And again, we get the same value. So this graph has two parts to it. From the y-intercept to the left, the graph is increasing as we go right to left. And then after that, it stays the same. So we're going to have one piece coming up like that, and the rest would be flat. And there's arrows on both ends because there's arrows on both ends of the original graphs. But now the domain and range, there are some differences here for sure. If we look at the graph of h, there are no restrictions on x. The domain would be all real numbers. The graph goes left and right forever. So -infinity to +infinity. There is a restriction on the range. If we look at the first graph, the graph of f, the range there is that y must be greater than or equal to 0. On the second graph of g, there are no restrictions on what y can or cannot be. But when we look at the graph of h, the restrictions there is different. This graph goes down to a minimum of +5, it looks like. And so the range of this would be from +5 up to +infinity. Okay? Now, part D says, is f take away g at x equal to g take away f at x? And then if not, what are similarities and differences? Well, we already know what f take away g is. We did that one already. That is the absolute value of x, take away x, plus 5. Okay, but what about g take away f at x? So that would be g at x take away f at x. G is the equation x take away 5. Take away f at x, and you see we don't really need brackets there because there's only one term. If I rearrange the terms so at least they're in the same order as the previous equation, the negative sign in front of the absolute value of x would stay there. The x is positive, the 5 is negative. If we compare that to f take away g, they're not the same, but they are in fact opposites. You see, if you take out a common factor of negative 1 out of this, then that equation inside the brackets is the same as f take away g at x. So g take away f is the same equation as f take away g, except there's a negative 1 in front, and that negative 1 is an a value of negative 1, which means that the two graphs are connected by a reflection over the x-axis. That's what happens when a is negative, right? Reflection over the x-axis. So as a conclusion here, we can say that g take away f at x is equal to negative f take away g at x, which means that they are connected by a reflection over the x-axis. Okay? Again, you have to remember that when you subtract, order absolutely matters. When you're adding the two functions, order doesn't necessarily, well, wouldn't matter. But when you're subtracting, it absolutely does. All right, so tomorrow we'll look at quotients and products. You don't have the 10.1 assignment in your booklet? No, but you don't have the 10.1 assignment in your booklet?
Yeah.
It is there? Okay. It's just not on this copy that I have. So that's what you're going to work on, that 10.1 assignment. You've got that example 4 though, right? So let's do that really quick. Actually, we'll do it tomorrow. I'll have to change it so that I have that question up here. So we'll start today doing that next example. I don't think there's anything like that on your assignment. I don't think. No. So I'll get the answers, solutions posted for 10.1, so you can check your answers. And then, like I said, Wednesday we should be done this chapter. We'll do 10.2 tomorrow, and then 10.3 on Wednesday, and then Thursday we'll start perms and comms. Okay? I sent a bunch of stuff out for photocopying today for review for the final exam, diploma exam, so I'll start handing that stuff out to you as soon as it comes in. Probably not. I wanted to take the time to make sure you get everything done and hopefully have some time to review, or as much as time as possible. Yeah. Yeah. That's okay, I can get it. Thank you. Yes. Yeah. Yeah.